Okay, well, thanks. I just discovered that your projector has less than phenomenal resolution, so let's see if this will work in some way. Okay. Let's just try to do it this way. Can you see this? Can you projector just do this one? Tiny bit? Okay, thank you. Everyone can see this? Thanks. Okay. So let's see if I can find it off. So as we were coming back from lunch, we were introduced to a form of hazing at Swedish institutions. Apparently when the new students come in, Swedes have taken to copying the United States, which itself copied the British, and so students are subjected to all sorts of humiliation. The incoming students are subjected to all sorts of humiliation. And the practice is known apparently as nulling, which literally means zeroing, which I guess literally means humiliation to the point where the incoming freshmen are ready to subject themselves to whatever comes next. And in Sweden, apparently, KTH is one of the centers of this, along with Chalmers and more recently Uppsala. And all of these places are known for out-of-control drinking and partying, often resulting in participants losing consciousness. And so I just wanted to make an obvious remark that this is something to be seriously explored at Nordita as new participants come in. So, now just a second, I have a problem with my electronics. Give me one moment. I know, but it's more complex than that. However, I appreciate your input. Okay, so here is the subject of my talk. It is a discussion of high temperature superconductivity as it stands now after the discovery of iron-based high temperature superconductors. The science blockbuster of last year, officially by count conducted by the Web of Science. They have a particular algorithm for this. Iron-based superconductors have been ranked 6th just after swine flu for citation among scholars, and this is of course a wonderful statement, no comment needed about our field. Basically everything on this list is biomedical research except for number 1 topic on the list, which is exploration of dark matter, and also graphene appears there, which is another testimonial to that great field as well. As soon as these iron-based superconductors appeared on the scene, a trillion, billion, many billion-dollar question arose, which is how to make 100K iron-based superconductor. I just mentioned this to you in case you have some brilliant idea of how to accomplish that. And the reason for this is that material properties of these new systems are superior to those of copper-based high-temperature superconductors, even though their transition temperature is still quite a bit lower. If one could push it to about 100 Kelvin, or at least substantially above temperature of liquid nitrogen, one will be in excellent shape for all sorts of various applications. But no one up to this point has succeeded in doing that, and the top transition temperatures are about 58 Kelvin, just below 60 Kelvin. Of course, immediately, $100 question arose. which is what is the theory of iron nictates. $100 is a typical bet for a dinner at a distinguished fancy American restaurant with wine. And so what is the theory of nictates? This is all, by the way, market-based supply and demand issue. Nobody knows how to answer the $1 billion question, but of course everybody knows how to answer what is the theory of iron nictates question, and everyone and their uncle, including some of the people in the audience, have jumped in and tried to formulate their own view of what's going on in these materials. And I'm going to be biased a little bit in a particular direction, but I will try to give a reasonably fair assessment of where the field is right now and what's interesting in it.
What's weak coupling double plus mean?
Weak coupling double plus is like C double plus. It's depending how you want to interpret it, it's like some people say that C double plus is the grade that was received by the creators in high school in their math class. It's a basically souped up weak coupling. People have done any version of weak coupling imaginable on this problem, and we've actually heard about the spirit of this approach from previous talk by Professor Raghu. So people have all sorts of approaches based on weak coupling renormalization group, Gell-Mann law, functional renormalization group, numerical, any which way you want it. This problem has been addressed, and the results that people have obtained, by and large, show some consensus. So double plus means really fancy, signifying the hope of those who subscribe to this approach that it can be used to access moderately correlated regime that nictates are in. Okay, so I'm going to, as I said, give you a little rundown of this field. First, I'll explain what these materials are. Then I will discuss a little bit about their superconducting state, so you can get some idea what is exciting and interesting in phenomenological arena. Then I will discuss a minimal model of this problem that I like and that by now has some fans, although other people may have slightly different model. And then I will describe really kind of complex features of this within this weak coupling double plus approach. So this is the history of superconductivity. It has been a long and painful process since 1911. By the way, remember, next year is the 100 years centennial of discovery of superconductivity. There's going to be all sorts of events. One of these events is a glorious workshop at Center for Physics in Aspen, Colorado. And I happen to be one of the organizers, so I strongly urge all of you to apply. Remember, if you don't apply, you don't get in. Please make sure by end of January, early February, there's a deadline on the Aspen. You just type Aspen Physics, and Aspen Center for Physics comes out. Make sure you apply, and you know who I'm talking to. There are some of you here who have to be there. Okay, good. So up to basically 86, the story was a story of many people trying to push laboriously transition temperature a little bit up. Among most successful was Bernd Matthias, and it is his material, niobium-3 germanium, that is a record-holding material with 23 and a smidgen Kelvin. Many of these materials today are used to make superconducting devices, particularly magnets. And we can fairly describe this as a rather stone age of superconductivity. Then comes the copper age, the discovery of copper oxides, which really was quite a revolutionary development. And to this day, copper oxides, mostly the ones that are incredibly poisonous, remain record holders for high PC. Under pressure, one can reach 160 Kelvin. You see, it's a very high transition temperature, and commercially, commercial refrigeration at a liquid nitrogen temperature is a solved problem. But these materials are terrible materials. They're basically ceramics. It's like using your grandmother's china to make cables. They are just not very good. People make very complicated tapes, and they are in fact very poisonous. And people, those who dare, use exclusively their graduate students to work on it. Finally, in 2006, there was a discovery of a superconductor of this iron-based family at 7 Kelvin. Then the same group of Professor Hideo Hosono at Tokyo Institute of Technology, pushed transition temperature in this system to 26 Kelvin. And then finally, by spring of 2008, we had 58 or so Kelvin in iron arsenic class of these materials. And that's, of course, where tremendous excitement started. And this brings us to the Iron Age. I just want to mention, for those of you who are interested, for a brief moment, iron discovery of high temperature superconductivity in iron nictates induced the greatest web frenzy in history of condensed matter. Even experimentalists, who otherwise are known as sober, serious people in our field, started just posting everything on the web as fast as they possibly could. So for instance, in a single July 2008 day, there were 17 papers on nictates on the archive, and this actually rivaled the famous Bagger-Lambert revolution in superstring. Of course, that Bagger-Lambert revolution was like 17th revolution in superstring, so that doesn't count in a way, but it is a bit of a pride-inducing. Nictates, I just want to mention this, are of course well-known elements: phosphorus, nitrogen, antimony, bismuth, and of course arsenic. The name comes from Greek for choking and suffocation. That means you don't want to stick your head in an oven full of nitrogen. You don't want to take lots of arsenic, although I'm told there was a video on YouTube that got taken off of Chinese graduate students licking iron-based arsenic superconductor to illustrate just how strongly arsenic is bound. Apparently arsenic is very strongly bound in these materials, so you can lick it. I don't know if I would chew it, but apparently it is very strongly bound. By itself, it is a terrible news, and many major institutions in the United States, particularly major private institutions, have decided not to work in their labs with arsenic, because all you need is one undergraduate who gets sick, and then your multi-billion-dollar endowment is gone. And so these materials are well known in making so-called 3-5 semiconductors, and I mention this to you only because it is this quest for band gap engineering of semiconductors, changing the size of the gap so that you can basically change the color of various devices, that in fact led to discovery of this material by Professor Hideo Hosono. This is their original paper, and at Tokyo Institute of Technology, they in fact produced first the following low TC version of iron phosphorus, so-called 1111 or 1111 compound, and then they quickly pushed TC to about 26 Kelvin, and they got a deserved notice in a Japanese paper. But then, of course, it was iron arsenic compounds that pushed transition temperature eventually to the range of just below 60, and that came from a Chinese group of X.H. Chen, a future president of China, who actually had 3 Nature papers in a year on this subject, and immediately everyone and their uncle got into this field, as I said, and there was a flurry of Nature papers. If you're thinking of publishing a Nature paper on iron nictates, it's way too late. No one can publish anything. In fact, the exact solution of a multi-band model in any dimension, I doubt it would be publishable now. But early days, you could publish anything. I'm even told that some of these papers are not entirely wrong. So this is a list of about a third of known compounds. You cannot fit more on this, and I stole this from Jenny Hoffman. And this shows 2 basic, most interesting structures. 1111 already mentioned, and 122. This 122 material has TC of about 38 or so Kelvin, And its main significance is that one can make very large, very good single crystals. So lots of modern experimental work is done on 122. This is a record holder with about 58 Kelvin transition temperature, but it's quite difficult to make single crystals. There are some single crystals, but they're not easy to make. There are also 1,1 class of compounds, which are really not iron mutates, but iron chalcogenized. These are iron, tellurium, and selenium compounds. Their TC is lower, and then there is also 1,1,1, 3 ones compounds. These are the major 4 categories. Now, let me tell you a little bit about the similarities and differences between iron-based and copper-based high-temperature superconductors. In cuprates, the basic action, superconducting goings-on, are supposed to come from copper O2 planes, and similarly in the 1111 and 122, it is the iron arsenic planes which are essential for superconductivity. Of course, both of these materials have d electrons in key role. Both copper and iron are 3D transition metal materials, both are, as I said. And it turns out in their phase diagram, both have antiferromagnetism and superconductivity in close proximity. There are many differences, however, and it is these differences that make people very excited, because once you have different forms of high-temperature superconductivity, then of course both the theoretical mechanism that leads to this might be different, and of course opportunities to raise transition temperature much higher might be there. And this is, of course, where the excitement comes from. And so that's what I will talk about in what follows. The main difference really comes from a very simple fact that iron is a 3d6 the electron orbital configuration, whereas copper is 3d9. That means you can think of copper as having 1 hole in the d orbital, whereas you can think of iron as having 4 holes or 6 electrons, and that means in the case of copper it's an odd single hole problem, whereas in the case of iron it's even. Odd and even number of electrons has big consequences in condensed matter physics. In copper oxides we can think of writing an effective single band model that describes how this hole moves around. In fact, that's where most work has been concentrated when we study copper oxide. Once we have 4D holes or 6D electrons, we really cannot write an effective single band model, and we have to worry about many bands. And so that is a first important difference. Second, let me mention that in copper oxides, most people believe that, there is very solid experimental evidence for it, that the parent compounds of high temperature copper oxides are Mott systems, meaning that, of course, it's very difficult for electrons to move around because as you try to move them around at half filling, meaning that there is 1 hole for each copper site, you have to pay a penalty in this Coulomb renormalized clean Coulomb repulsion U, and that penalty costs you energy. If U is sufficiently large, the system at half filling will not behave as a metal, which would be a prediction of a band structure, but in fact will be an insulator due to these strong correlations. It will be, furthermore, an antiferromagnet, because this virtual hopping from site to site causes spins to order antiferromagnetically, so they can take advantage of the virtual hoppings, which lower ultimately the overall energy of the system. And in fact, that's experimentally true. At half filling, copper oxides are basically very strong insulators, and only upon doping they actually become superconductors. I stole this figure from the upcoming reviews of modern physics by my colleague Peter Armitage, and Rick Green. So take a look at that. Maybe it's already out. So it is necessary actually to dope them. And of course, when you dope these materials, then there is more room for electrons and holes to move around. And so this is the phase diagram of these materials. Hole doping and electron doping is not the same. I will not talk about that because there is no time, but they are significantly different. And particularly for hole doped materials, the effect of Mott correlations appears to be very significant. And this issue of how Mott insulators turn into superconductors in this so-called pseudogap regime, where the doping with holes is very light, is one of the great challenges of modern condensed matter physics.
What's real? Just a sec. I'm going to apologize. From this picture, it looks like if you dope with electrons, your superconductivity is better. Is this really true?
It would appear that this is the case from this picture. And in fact, in a couple of compounds that can be both electron and hole doped chemically, it sometimes is the case. But in fact, if you plot all the compounds, not all of them can be taken into both hole and electron doped regimes, then superconductivity on the hole doped side is above superconductivity on the electron doped side. And in fact, superconductivity on the electron doped side, in general, according to quite a few workers in this area, is perhaps easier to understand and maybe closer to a regime of weak or moderate correlations than the hole doped. Many people believe that hole doped, in fact, which is where TC is the highest, in fact, is closely related to effect of Mott physics. This is a drawing by an artist who obviously is not a physics Raffaello, but it's a nice drawing. Thank you for clarifying that. So now I notice that in these talks people take as much time as they want, and so I'm not going to take as much time as I want, but I will take a little bit of time. And so as I ran out of time, I give you dispensation in advance. You can just leave. And if at some point you will think that I spoke too much, and then you will just stop me. But I just want to tell you a few things, because some of you, of course, are grizzled veterans of high-temperature superconductivity, but some of you are not. And so I just want to tell you a few things about the subject of high-temperature copper oxide superconductors. I'm not going to go into it in any depth. And so here is a little problem of superconductivity. In fact, you can turn that question from a previous slide around, and you can ask how correlated superconductors turn into Mott insulators. And so this morning we had a very nice talk which basically looked at this problem from the side of V-coupling. And apart from various technologies that we like better than other technologies, the physics of this is understood to a reasonable extent. There is a Fermi liquid, there is some basically overall repulsive interactions, and these interactions can produce superconductivity in certain channels. And for doped single band of a Hubbard-like, or so-called TJ model, at some doping, it will be dx squared minus y squared superconductivity. So many people think that that this is not just imaginary theorist phase diagram, but that this is a situation that takes place in overdoped high-temperature superconductors. So this is a weak coupling and can be solved by some combination of BCS, Eliashberg, Mead-Dahl renormalization group methods. Then we get into a very strongly correlated limit of superconductivity. And there the problem arises, even though the pairing tendency to form Cooper pairs is present, the ground state of such a system does not have to be a superconductor and could be something else. That's a problem that's difficult to solve. By the way, on our journey from weak to strong coupling, we can take a roundabout way, the way of temperature, and the moment we go to finite temperature, we immediately get some thermal fluctuations. Please observe that on a weak coupling side of this, there is no such thing as quantum fluctuations of a BCS superconductor. Once the interaction is repulsive in every channel of interest, we just have a Fermi liquid. And Fermi liquid is not a fluctuating superconductor, not by any stretch of imagination. But at finite temperature, we can talk about fluctuations, and these are always, it turns out, phase fluctuations. This is all known to excruciating degree, although not always remembered. And so the interesting thing takes place in this strongly correlated regime as we approach some Mott limit. Mott here means very general limit in which correlations that want to stop electrons from moving around become very strong. So kinetic energy is going to be running very low in this regime. When that takes place, the ground state itself can be destroyed by strong quantum fluctuations. And those, in case of superconductors, often come in form of quantum vortex, anti-vortex fluctuations. Now, this is the ground state in which, as I said, pairing correlations are strongly enhanced, but the ground state is not necessarily a superconductor. What is this ground state? Well, that's a big question because it's closely related to the question of what is that pseudo-gap regime and what is the fate of copper-based high-temperature superconductivity when lightly doped with holes. Lots of people have proposed lots of beautiful theories. They have lots of relation to each other. They often take form of gauge theories, quantum electrodynamics in 2 dimension, chiral symmetry breakings are heard of, ADS-CNT, this is anti-de Sitter, condensed matter theory rather than anti-de Sitter, CFT, which is a conformal field theory. Basically, these are various forms of non-relativistic ADS-CFT correspondence that people work on in hope to somehow capture behavior of a very strongly correlated superconductor or system of this kind. And there's a cast of characters that have contributed to this, and I've not put everyone in here by any means, but any one of these people can tell you long stories about what happens there. So, I mentioned already there is no such issue at weak coupling because that's just a familiar word. Notice that optimal TC here is basically determined by such quantum fluctuations, because the reason why transition temperature takes a dive here is because it's approaching this quantum disordered ground state of some kind. Okay, as I said, this is a very, very quick detour to copper-based high-temperature superconductivity. There is some indication that something of that kind is taking place. These are famous Ong et al. Experiments from Princeton, which first of all show very large Nernst effect well above TC in this pseudo-gap regime, and large Nernst effect is an indication of very strong superconducting fluctuations. In fact, Professor Ragu worked on that. You can ask him, he's an expert. They also see a quantum diamagnetism of the size that is typically a signature of superconductivity alone. Once diamagnetism goes above a certain size, you can pretty much be sure that what you have there is an incipient superconductor, because most materials in natural units have extremely small diamagnetism. So there are many other experiments along these lines that indicate that something like this is going on, meaning superconductivity destroyed by quantum disordering. Very nice measurements of superfluid density by Tom Lemberger group at Ohio State. They show a suppression of measured TC in films as you approach this critical point, if you will, on the underdoped side. And they measure that superfluid density and correlate TC to superfluid density at 0 temperature. And it turns out they scale in a very special relation, which indicates that, in fact, the magnitude of TC, superconducting transition, at finite temperature is, in fact, dictated by the superfluid density at 0 temperature in a relation that is characteristic of quantum superconducting fluctuations. Unfortunately, one cannot say much more about this because 2-dimension happens to be precisely the dimension where quantum fluctuation, whether they have z equal to 1 or z equal to 2 or z equal to 7, dynamical critical exponent does not change this relation. But it tells us that there are some very strong quantum critical fluctuations of a superconductor. Interestingly enough, at lunch, there was a discussion of possible quantum spin liquids in some other systems. And here in high TC, there is a very nice measurement of heat conduction in the underdoped regime, where we see a heat conduction which, inside the superconducting state, is due to nodal Bogoliubov-Dejean type of excitations, continues along outside the superconductor. Once you get out of the superconducting dome, these nodes appear to be there. This is a set of data from Louis Taillefer group. There is a similar set of data from Brookhaven. On the other hand, there is a very interesting set of measurements of so-called de Haas-Van Alphen oscillations, which indicate a presence of perhaps some kind of Fermi surface, although very small Fermi surface, in copper oxides on this underdog side in a pseudogap state. And this has been attributed to pockets, potentially, pocket-like Fermi surface that perhaps is left in the wake of antiferromagnetic ordering. On the other hand, there are even more recent experiments that clearly show nodes again in this pseudogap regime, just like the heat conduction does. These are ARTES experiments from Argonne. And then finally, there is this very interesting experiment coming from National High Magnetic Field Laboratory that we just posted last week, but the preprint has been circulating around. It has been sent to a glorious journal, and we'll see what happens. And this experiment shows specific heat in high magnetic field. This is a detailed paper. You can go look it up. The first author is Riggs, and you can search for Wafek or Bobinger as co-authors. I just want to leave you with one thing here that you may find entertaining. Here is the data on specific heat at very low fields. And here you see a square root of H dependence, which is characteristic of nodes in a D-wave superconductor. But that square root of H dependence continues basically the same up to enormous fields, 45 Tesla, long after the superconductor has in fact stopped superconducting. So this is actually a rather strong evidence for presence of a very large D-wave-like, pairing-like pseudogap in the pseudogap frames.
Where's the HC2 on that?
Right here.
The reversibility field.
So as Leo Jarzykowski knows very well, what is HC2 in a strongly correlated fluctuating superconductor? A mean field HC2 by fits of this type would have been 0.
I see. Okay.
In fact, Sebastian et al. Estimated in their oscillation experiment to be around 150 Tesla, or maybe even 200 Tesla. This is actual point where the material becomes resistant. So this regime, in the parlance of this field, particularly of the experimental field, is called flux flow, or flux motion regime. Notice these are very low temperatures. So this is not flux motion due to thermal agitation. This has to be quantum motion of vortices and their anti-vortex relatives.
So do you know what are the temperatures for this?
So, well, these are millikelvin.
Okay. So really, okay.
These are millikelvin temperature. So this is basically 0 temperature. Okay, so
Can I ask a question?
yes.
Weren't there some STM experiments also which indicate pseudogap in the appropriate regime?
Yes, exactly. So there were, in fact, some of the earliest evidence for, I will show it in a second, for pseudogap came from STM experiments. And in fact, there is a strong evidence from STM experiment to indicate that this D-wave-like pseudogap extends outside of superconducting state. However, there is not a problem, but there is a certain debate going on in STM community as to how should one interpret the bare data, the raw data. And you see there is this process of symmetrizing the data, which people have challenged. And so there are also procedures which do not now symmetrize the data, but actually look at the raw data both for above and below, and then try to reconstruct both positive and negative bias data in STM. Typically what they obtain is that for low energy, the symmetrization is warranted because the spectrum is symmetric. I mention this because a plus-minus energy spectrum is a signature of pairing correlations. But for higher energies, that's not clear. So I just did not put it on, but if I had more time, I would have put it on, and thank you for pointing that out. This is an enormous area of research, as you know, so yes, I should have mentioned STM data. And so if you want to know everything about STM data, you just type Shamus Davis or Jenny Hoffman or Ali Yazdani in Google or Archive, and everything will come out, including the references to other workers in the field. So I'm now running a lot beyond my time. But let me just keep going. So I just want to tell you what's the problem here. So to understand what the problem is, it's useful to look at the case of negative U Hubbard model. Like, for instance, several speakers, including this morning, have illustrated to us how we can solve negative U Hubbard model at weak couple. Then we agree at general doping, general shape of the band, this is a superconductor, minus the 2D provisions of Costelli-Salles and so on. What happens when we have negative U, but the negative U is very strong, meaning it's the strongest energy scale in the problem, larger than kinetic energy or any residual Coulomb interactions that are due to insufficiently screened original bare Coulomb interaction. When we have that, then we have basically a BC limit. We have little Cooper molecules with electrons spin up and down sitting on the same site. And then, of course, on the lattice, we can solve this problem. And the solution looks like this. We either have a superconductor, where these Cooper pairs are floating around on the lattice, or they get locked in into a charge density wave of Cooper pairs, sometimes called pair density wave. And the way they lock in, because once their kinetic energy is low, then residual Coulomb interactions basically lock them in into some particularly preferred magic fillings depending on the underlying lattice. And so, if kinetic energy is large, we will in general have this, the superconducting state. If kinetic energy is weak, we will have this. And so this can be understood in various ways. There is lots of numerical work also on negative U Hubbard model and related models. It can also be understood using something called duality, which is a beautiful subject of which I will not talk about at all. But understanding it using duality in this context does not necessarily bring anything terribly new. It's just, one can just do it using, the wonderful thing about duality is it allows theorists who don't have really big computers to actually do something that's still interesting. So, like B. But as I said, in this context, it does not really bias something that you would not be able to see by using other methods. I want to tell you what this duality is.
So, but in a previous report, this is just a Bose-Hubbard, effective Bose-Hubbard superfluid insulator.
Yes.
In
yes.
molecule.
And it's understood every which way. Yeah. Okay. So here I just want to show you what is this duality, what does it deal with. So we can take now this very negative U Hubbard model where this energy is larger than any other energy, including kinetic and residual Coulomb interaction. We can then fix the amplitude of delta, which is like a gap parameter. We fix its amplitude, but leave its phase to hang. And fixing its amplitude is good because it always buys us this binding energy of minus U. Then we put a phase here. Then naturally we think of phi I minus phi j as a gauge field, which is coupled to electrical charge. This gauge field is on a lattice. Phi I minus phi j makes this gauge field compact. But that's okay, we know how to deal with that. And then we can use this duality, as I mentioned, where the fluctuations of this phase correspond to central mass motion of Cooper pairs. And here is our famous gauge field. We take 2 plus 1 derivative. The plus 1 is time direction of this gauge field on a lattice, and it's equal to 0. This is very good because it tells us that whatever are the configurations that these x5 phases take in 2 plus 1 dimensional space-time, they can be described as configurations of vortex and anti-vortex packets. This is basically a conservation law for vortices. Does that make sense? A little bit. This means that vortices behave as lines of magnetic field on the lattice, on this 2 plus 1 dimensional lattice. Why is that good? Well, that's good because we now can say that this conservation of vorticity is in fact strongly related to conservation of Cooper pairs, which it is, and therefore we can treat vortices as quantum particles, just like we could treat electrons or Cooper pairs in a boson-Hubbard model as quantum particles. And this allows us to make some actually strong statements. Now, Cooper pairing can also be driven by a repulsion, as Professor Raghu showed us this morning. In that case, like say in cuprates, we have a D-wave-like order parameter. How can you get Cooper pairing from repulsion? Well, if the interaction is repulsive but concentrated in momentum space, so that it connects portions of the Fermi surface with a wave vector that's close to this green wave vector, then you can solve a gap equation, which now has an annoying minus sign here, so S-wave solution would not work. That's because, of course, interaction is repulsive. You can solve it by looking at a state like this. And so plus is always connected to a minus here, and vice versa. And this solution allows you to get finite transition temperature and finite superconductivity, finite gap at zero temperature, even though your basic interaction is repulsive. This is what corresponds to a negative eigenvalue lambda from this morning talk. Why would something want to be superconducting from repulsion? Well, it turns out, if you remember this morning's talk, as Professor Raghu showed us, all of those states that were favored, including the states that were most favored, had a node at the point where they would have to pay a penalty of U. So what superconducting state does, rather than making these nice Cooper pair molecules due to attraction, what it does, it allows electrons to avoid each other efficiently, and sometimes most efficiently. So in fact, superconducting state coming from repulsion is a trick to go into a state where repulsion, negative effects of repulsion are minimal. Okay, so now you can get superconductivity from repulsion. Here is your pseudogap that you were asking about. This is an STM data which shows here is a real TC, but the gap-like structure in cuprate seems to persist to much, much higher temperatures. And so this affects, of course, strong fluctuations in such materials. So in correlated superconductors, we have pairing not due attraction, not due to attraction, but due to repulsion, allowing us to avoid, to reduce this repulsion as much as we can. Why is that a complicated problem? It's a complicated problem. And this transparency shows that it's very complicated. I lifted this transparency straight out from Phil Anderson's talk at KITP last year. We can basically try to solve now a problem exactly the same as before, but with large positive U. So we take U, this energy scale, to be the highest energy scale, but most repulsive. So this is a strongly correlated, not weak correlated regime. And then we get some effective Hamiltonian, which is a TJ Hamiltonian, and there'll be lots of extra terms coming from T prime, coming from Coulomb interactions that were not sufficiently screened, and so on. But this Hamiltonian carries a projector which tells us that there is no doubly occupied sites, because that costs too much. And so now, as Anderson et al. Have suggested, we can take a D-wave, a superconducting state, that would be a solution at V coupling, apply this projector that eliminates doubly occupied site, and that way construct a ground state. And that's a very good strategy. In fact, what one can do is a phase diagram drawn by Anderson. It's very important here that he makes line which denotes vortex length. It does not touch superconducting line. So I'll direct you to that. As I said from a previous slide, this is a BCS wave function, and then we just apply a projector BCS wave function for D-wave superconductor. However, inside of this phi, there is delta. In the mean field solution at strong coupling, this delta for D-wave superconductor of this kind is plus delta along x direction on each bond, and minus delta along y direction on each bond. This will give you dx squared minus y squared superconductor. But in general, delta is a complex function, and therefore it also has a phase. So I fixed its amplitude into this delta minus delta D-wave pattern, and then we consider what it's phased up, just like we did for negative U. Well, something interesting happens here. As we approach not insulating limit, where x equals 0, and therefore there is no motion around because we just have one electron per site or one hole per site, And any motion would have put two holes, one with spin up, one with spin down, on the same site. For infinite U, that's not possible. Therefore, this theta will start fluctuating. And the reason for that is just an uncertainty relation between the phase and the particle number. If particle number fluctuations are completely suppressed, phase fluctuations will go haywire. And so I just do some complicated harmonic oscillator problem. As you all know, theoretical physicists can solve any problems except linear harmonic oscillator. And so, of course, other people have looked at different linear harmonic oscillator problems in different contexts here. But it is the fluctuations of this bond phase that now have to be understood to gain some insight into strongly correlated D-wave superconductor. And here's the same story, except that gauge field now is a bond phase theta ij. It's not a difference of side phases. Actually, we can understand this problem in a similar way. We just take two sublattices on a square lattice. One of these sublattices will changed by particle-Hall transformation, and then this Hamiltonian simply becomes something that looks more familiar. The pairing term becomes hopping term, and this theta ij is just like a gauge field in a hopping term. And the hopping term becomes pairing term. Huh? That's easy. So kinetic energy is just like pairing term. And now, if we are very close to half filling, kinetic energy on average is extremely small or vanishes. That means this will fluctuate like crazy. On the other hand, if we dope the system, so kinetic energy grows on average, this fictitious pairing term acts as a Higgs field. This basically means that our fictitious superconductor is immersed into stationary Higgs field. That suppresses its fluctuations, and eventually we get a D-wave superconductor. So, this cannot be solved exactly, but it can be studied, and I will now wrap up, because everybody's eyes are glazing over. I will just show you what happens. It turns out bond phases are very different from side phases. Bond phases describe... Hi. Yeah, of course. So even people who are not here are annoyed and provoked by my talk. The fact that we have a bond phase here tells us that this is a non-local problem. Cooper pairs are non-local entities, and that's actually very important when we construct this D-wave duality. It turns out, I will just give you the physical punchline, there are monopoles in this bond phase, and what these monopoles mean is that the vorticity, in this case, is not conserved. You can have a vortex that comes to a point and then just radiates its vorticity out. So because this is a bond phase, not a side phase, vorticity is not automatically conserved. For people who enjoy duality, this means that Cooper pairs are not automatically conserved. And that means that Cooper pairs, translation to physics, Cooper pairs can in fact fall apart. They are held together by kinetic energy. If there is not enough kinetic energy, if there is not enough motion, Cooper pairs will just fall apart. Why? Because in a system where superconductivity is brought on by repulsion, there is really no deep down BC. You cannot make little molecules because there is no attraction. Okay? So when you push this system in a strongly fluctuating regime where there is not enough kinetic energy, instead of sitting on lattice sites, Cooper pairs will just fall apart. And then an interesting question is, when they fall apart, what do they become?
Can I ask a question?
Yes.
So what the mechanism which couple monopole to vortices?
Which is the mechanism that?
Which couple vortices with monopoles?
Well, it has to do with the fact that theta ij, if you take bond phases on a 2+1 lattice, and you allow all possible configurations to take place, there are configurations that are purely vortices, and then there are configurations that are not. So it's not that they are part of the same fluctuation picture, they are part of the same variable. But once you have this Higgs-like term, this kinetic energy come in, monopole configurations are suppressed. So in fact, I have a little picture which I can show you, which shows a phase diagram, not this picture. I will jump through it because there is no time because I have to tell you about nictates in 5 minutes, which I can do. Anything worth talking about can be explained in 5 minutes. So here is the picture, you see. Basically, once you include fluctuations of these bond phases, it turns out they can be divided into fluctuations that can be described using only vortices, and fluctuations that cannot. And this contains the monopole sector. And when you allow all possible fluctuations in that generic Hamiltonian, you in fact get 2 lines in the phase diagram. One line is when this unbinds, whereas this is still ordered. That kills superconducting order itself. But it turns out you still have some good way of defining Cooper pairs, because vorticity is still conserved at long distances. So Cooper pairs are well defined at long distances. And then eventually, this part that does contain monopole sector blows up, and Cooper pairs fall apart. And once Cooper pairs fall apart, guess what this state is? It's an antiferromagnet. So this is a picture of D-wave-like duality, and here is the basic phase diagram.
Can you just explain what defines these 2 pieces of theta? You know,
yes, that's a very good question. I had that on one of the previous slides. So
they literally appear next to each other.
No, they're just 1 theta.
So yeah, so it's the piece
Here it
which
is.
curl of.
So you see, imagine you have a 2D lattice. There is obviously n site phases, where n is the number of sites. But there is 2n bond phases. So in fact, not all bond phases can be reduced to site phase, like in 1D. And so one way, which turns out is the natural way to define center of mass motion, this part, that can be represented by site phases, is this. It is not unique, because there are several different ways that in a long distance continuum limit behave the same. But this turns out is the best. And these are some site phases now. These are basically phases describing center of mass motion of Cooper pairs, which are extended objects, but nonetheless have well-defined center of mass.
And so the other piece of theta is a correction to this somehow?
Everything that's left out. Yes. And you can show that this is a good definition, because in the long distance limit, this couples to charge 2e.
Okay, so this piece gives you vector potential, the gradient of the angle.
Yes.
And then that's why curl of it is
0.
0.
In reality, of course, curl of it is not ever 0. It's just that its fluctuations are suppressed. So you always have things like this. But the distance between this and this is always small. In other words, these are always bounded. So at long distances, longer than a binding length of each, you can still talk of Cooper pairs and vortices in a dual relation.
So I just have a question about this whole way of doing things, which, as you know, I like very much. But
Yes.
does it hold in the limit where u is infinity? Where
I couldn't hear you, sorry.
so you require u to be large but finite,
Yes.
so that you have a j.
Yes.
What happens when u is infinity?
Then it doesn't work because you don't have J.
So then
So,
what's the...
then it's Nagaoka theorem and everything. The system is a ferromagnet, basically.
But that's only for one hole, right? What happens if I have some finite concentration?
I cannot solve it this way at all, because remember, my delta is tied to J. So I cannot, this is not applicable. So, because you see, J, in some sense, is my high energy. So if I put that high energy to 0, I don't have a theory above it. I mean, it's of course, perfectly good question for real physics, but I rely on having finite J. Okay, so does that answer your question? So I spend all this time to show you just basically how difficult this problem is. And there's lots of technology that goes into it that has been developed by people over time. And I'll be delighted, this is a theoretical workshop, I'll be delighted to talk to you about if you are interested. But I discovered recently most people are just not interested. Because it's so difficult and one can derive few really rigorous results. And experiments are not entirely clear. So consequently, I'm just going to abandon this. And for the remaining part of the talk, I'm going to tell you about something we know how to do, which is iron nictates. Now their life is much easier. First of all, because of that odd and even count, life is easier. Iron nictates are supposed to be semiconductors, as I told you already. But when you make these semiconductors, every once in a while, you end up with a bottom of the conduction band being below the top of valence band. In other words, you get a semi-metal. These electrons from here going to, from here going to here, and you get some hole pockets and some electron pockets on the Fermi surface. And then, of course, the problem of correlations is different, because now most of these pockets correspond to bands which are either almost full or almost empty, and it's easy for electrons or holes to get around. They don't have to be hitting each other all the time. And so, just on these general grounds, we expect iron-based high-temperature superconductors to be less correlative than their copper cousins. Is that pretty clear? The effective repulsion is less. The half filling that we have to deal with in copper oxides is the worst for this kind of knot correlations. Here's the phase diagram. There is a coexistence of spin density weight and superconductivity, just like in cuprates. People argue exactly what is the shape of this, but they are surely very close to each other, the two states. But very importantly, unlike copper oxides, all the regions in iron dictate phase diagram, in iron arsenide phase diagram in particular, are metals. Remember that resistivity plot that I showed you in what now seems a very, very distant past? It turns out that, actually I'm going to open this door because it's so hot here. Is that okay? I hope that gentleman doesn't come. But there is more of us than him. So anyway, when you look at parent compound here, it turns out resistivity takes a little upswing, but then it just comes down as a metallic resistivity, even though you are in the order spin density wave state, in an antiferromagnetic type state. And of course, for superconductivity, you just get a standard metallic resistivity. So that's important. These materials are not in the Mott limit. Similar conclusion is obtained from ARPES, from the Haas-van oscillations, which have been obtained 2 months rather than 22 decades after the discovery of these materials. And they are very nice, reasonably well defined coherent bands, which are in rough agreement with, basically there's an overall factor of 2 or maybe 3 from band structure calculations. Here is a minimal model of these materials. I'm going to ignore everything but iron arsenic planes. And then I take these iron arsenic planes and, to coin a pun, I iron them out. And so iron forms a perfect square lattice. And then arsenic sits at the centers of the plaquettes of this perfect lattice. And in real material is up and down from the plane, is puckered in a checkerboard pattern. It turns out we can construct some tight binding description of this. And as I said, iron has 6 d electrons. The whole d orbital family, all the states are there, 5 of them. And it turns out all of them have to be included in some way because they are all reasonably close to the Fermi level. Furthermore, to make life more complicated, arsenic 4p orbitals are also not too far. So it turns out they give a contribution as well. There was a very nice model which was suggested by, in fact, Professor Ragu and his collaborators, where we include dx, z, dy, z orbitals. And this is, in fact, a natural thing to do because these are the most important orbitals, the ones that connect ions themselves. And of course, for theorists, this would be a delight because 2 orbital model is better than 5 or 4 orbital model. But it turns out this model has some very nice features, but it also has a bit of a shortcoming. It turns out to get a more realistic description, near gamma point, you need dxy orbital. Now, okay, 3, maybe a little contribution of dxy is okay, but it turns out near m point, you need a little bit of dx squared minus y squared. That's a really annoying thing. Patrick Lee pointed this out for one of them, we pointed out for another. If at least the extra thing that was needed was common for the two, but it's not. So you may then want to include 4. Once you include 4, as they say, once you don't clean your house for 4 months, when you don't do any housework for 4 months, it doesn't get any worse after that. So if you have to include 4, you might in fact include the 5th one. And so it turns out this 5th one doesn't contribute that much. But recently there has been a spate of papers by a Japanese group of Kuroki et al. Who actually argue that in fact you do need this orbital for all sorts of things. It's natural that they would want to have more and more orbitals because ultimately they are the people, when you have the most orbital, they can turn on their LDA, RPA scheme, and everybody, all other theorists in the field will just go and do something else, like topological insulators. So by having as many orbitals as possible, they're basically trying to corner the market. But at any rate, we'll make this problem still simple. Can I still go on?
Yeah, sure.
So you just protest. This is a free country, so if you have enough, you just shut me up. So as we'll see in a moment, how we take this complex multi-band situation that I promised in the beginning, how can we make this work for us and take advantage of this? So you compute the band structure, and a number of people have done that in various ways. It turns out you have indeed this whole pocket and electron pocket structure like this, the structure that was already obtained in 2-orbital model by Ragu et al. But then the orbital content is a little different here, and here is some parameters. We don't really care. The only thing that matters for us is that there is a considerable admixture of these annoying extra orbitals, and it turns out that precludes a relatively simple and beautiful orbital topology. So I'll have to worry about details, sadly. So this is a little slide that explains why Hund's rule, many of you, some of you have been born a long time ago, like me. And so you remember that iron is most often magnetic. In fact, typical iron oxides are incredibly magnetic. And that's because of the Hund's rule. When you have 6 electrons sitting on the same site, they will arrange themselves in the high spin state, so their orbital state, the orbital wave function, can be most antisymmetric to minimize the effect of local Coulomb repulsion. And a very important point in these iron dictates is that that fate of iron is avoided because of strong hybridization with neighboring iron and arsenic. The bandwidth is quite large, and that fate is avoided. So now let's construct a theory of this in 2 minutes. So here is our hole-like and electron-like features on pockets on the Fermi level. Now I'm going to borrow everything from this morning's talk. So first of all, I'm going to assume that these holes and these electron pockets are all identical, which they are not, but they are close to each other. I'll assume that they are all identical. If they are all identical, there is a particle-hole pairing susceptibility that diverges logarithmically at wave vector pi tau. This is not a Cooper singularity from this morning's talk. This is a singularity that has to do with the famous cross diagram in this morning talk, which in a featureless band is just doesn't have any particular singularity. But it turns out the heaven for logs in a particle hole channel is a multi-band Fermi surface with approximately equal in shape and number hole and electron pocket. That's heaven for logs. And it turns out you have a particle hole log like this, if they are really the same, and this particle hole log at wave vector n, which is pi pi, leads to logarithmic singularity, which is here calculated for actually more realistic shape, which then singularity is not really present, is cut off. And this strongly favors formation of density wave, spin density wave, or maybe even orbital density wave, because we have several hole and electron pockets at wave vector pi. This is the strongest tendency in this material. Here is a little picture of that. I take our semi-metal, and then I make particle-hole transformation. So I take this particle-hole pairing diagram and turn it into a fictitious Cooper case, and here's opening a fictitious superconducting gap, which is nothing else but a spin density wave, let's say, at wave vector pi pi. And this is exactly what is observed in this material. So here I had a little caricature of how we do this with real interactions. I will not bore you with this. Some of you are in the cold atom background. So all I do here, I just make particle-Hall transformation. And my Hamiltonian, instead of being Hubbard model with repulsion, becomes Hubbard model with attraction, which in 2 dimensions we know how to solve. And at any filling, with any structure, it's in fact a superconductor, and this superconductivity just translates in the real world into a spin density wave at light. So I will not bother you with this any longer. I just want to mention one thing. If we look at the original problem, when I made this particle-Hall transformation, I ignored everything else in the Hamiltonian except for terms like this. All these little dots I threw away. I use this to show you that without these dots, in the real world, this kind of Hamiltonian describes only spin density wave, and it has no superconductivity at all. This is a rigorous result. So any superconductivity which is electron-induced must come from the dot terms that I threw away. So now I have a little part where I talk about what is known experimentally. Since this is a theoretical workshop, we don't care about experiments. And so I will just, you see, life of condensed matter theorists is terrible, because all our beautiful theories are destroyed by experiments. And so we should learn from our superstring colleagues who really don't care about experiments. And so I'm just going to switch this. I'm just going to take this out, and I'm going to show you the part of how we can actually work out the theory of this.
You know that this sorts of professors are not interesting theories.
So that's exactly what I have in mind. So now I'm going to jump over the experimental part, and I go back to that minimal model. I notice something that annoyed us before, which is that the interactions, the orbital content around this Fermi surface is very, very complicated. These are various d orbital derived bands. As we go around the Fermi level, their content changes for hole-like pockets and for electron pockets in a very funny way. But we don't care about that. We already know that iron dictates are less correlated. They're not in a Mott limit as cuprates. And so we'll try to construct a multi-band description where this kind of complexity works to our advantage, actually. And the way we do that is here. So we assume that we can work in a moderately correlated regime. We write a generic Hamiltonian with generic interaction. This part you already know from our minimal model. And these are all possible interactions at the orbital level. This is overall Coulomb repulsion, Hubbard U1D orbitals. This is the Hund's coupling. There are many, many other couplings discussed by, for instance, George Savatsky in great detail. We couldn't care less about that. What we do, we find our hole and electron pockets on the Fermi surface, and we notice that whatever these interactions are, they will give certain contribution to the vertices, 4-point interactions at the Fermi level. And all of these interactions can be classified in several classes. First, they are flavor-conserving vertices. What that means, if the hole 1 comes this way, when the vertex interferes and there is an interaction, hole 1 continues this way. These are flavor-conserving. Then there are flavor-mixing vertices in what we call often particle-hole and particle-particle channel. And so whatever these interactions are, it is only these vertices that we end up with at the Fermi level. And so that's the only thing we have to worry about. So I now we just go and compute these vertices in some scheme. These are just some numbers. You don't need to care about that. And we indeed find, by the way, as I said, to no one's surprise, that the dominant interaction in the parent compound will be in the particle-hole channel and will lead to spin density. But then we also find these dot-dot terms. These are the terms that were missing from our Mickey Mouse picture. They are small, but their contribution violates certain symmetry, And now that symmetry that forbade having true superconducting state is lifted. And so these dot, dot, dots can perhaps give us something that's superconducting. Note in particular this term, which acts as a K-space Josephson term. It takes holes, pair of holes, and scatters them into pair of electrons. I know I should be ending, so let me do this very fast. Could these terms be closed for superconductivity? So we write some theory like this. Here is what those terms do. They basically create a resonance between hole and electron pockets. And then it turns out this kind of resonance can in fact lead to superconductivity. And it will be a superconductivity which has order parameter gap on hole and electron pockets with opposite sign. And the reason for that is because this G2 in general is repulsive. Now it turns out there are two types of this interband superconductivity. One is well known for many years. It has to do with the fact that we can have superconductivity in both pockets separately, and then this kind of interaction boosts superconducting transition temperature up. But this is a little different. This is an intrinsic interband superconductivity where without this term there is no superconductivity at all. And it's only through the action of this term that one gets superconductivity. This is a superconductivity which is repulsion generated. That's why, of course, we want to have delta switch its sign when we go between hole and electron pockets. And these are intrinsic interband Cooper pairs. They are neither in this pocket nor in the hole pocket nor in the electron pocket, but in fact they resonate in between the two. There is only one order parameter. The big problem here is that for this to work, we need this interband interaction to be stronger than intraband repulsion. Because there is still some intraband repulsion inside this hole and electron pocket. And this will never happen. This is unlike what Professor Raghu showed us earlier this morning, where the part, annoying part, that has to do with short-range structuralist repulsion is eliminated by the different symmetry state. In a P wave or D wave with the nodes, you just don't get a contribution of this kind. Here, the most prominent state is a state, this plus-minus type of state, where in fact, because these are generally not exactly the same at finite doping, these intraband repulsions are there, and they are big. So is there any way to overcome this? Don't pay attention to this. And jumping through things. Yes, there is. We do a very serious calculation. We start with the most symmetric model, which is U4 plus U4. We then add all the symmetry flavor conserving vertices, which is a good approximation here. And then in the end, we include these annoying but beneficial for superconductivity flavor mixing vertices, and we treat them with the renormalization rule. And when we do that, this is what emerges. You can draw diagrams. This is analog of G dot equals to G squared in matrix language equation that was written this morning by Professor Raghu. Remember now, however, instead of having Cooper pair logs that we had this morning, we now have logs that have to do with nesting between electron and hole pocket. So there is more logs, that means there is more equations. Some of these, by the way, don't contribute because they don't have logs. But in general, we can take all these relevant vertices, and we can solve those equations. They're very complicated equations. But I just write here a distilled version of what they are, and I explain it to you. This is the interaction that led to spin density wave. This is our Josephson resonance in K-space that takes pairs of holes into pairs of electrons and back. And U is repulsion inside each of the bands. These are the normalization group equations that they satisfy. These are the diagrams. The only thing I want to stress to you here is that these equations are coupled. And they are coupled by this particle-hole interband interaction that led to spin density wave. Let's turn spin density wave off. Let's turn spin density wave off. If we do that, this term disappears, and the equation in the Cooper pair, in the superconducting channel, looks like this. I told you it's like G dot G squared, but the sign here is minus, which means this runs into 0. The only thing we have here is a Fermi liquid. Or potentially, we could have a P-wave superconductivity at temperature of 10 to minus 78 Kelvin. Okay? So, from so-called cone latitude instabilities. But the only way to turn this around is to have, at the bare level, this Josephson-like term stronger than intraband repulsion. And that will not happen. This is where magic of renormalization group comes in. If you actually plot these flows, you discover that because these are coupled, as we approach spin density wave, of course, spin density wave itself diverges very strongly in the parent compound with very good nesting, like this, but it pulls this Josephson resonance with it, while the intraband repulsion just goes down. And so it's possible that at some low energy scale, the Josephson resonance that leads to this interband pairing, when renormalized, will go above the renormalized value of interband repulsion. This, of course, doesn't help at all, because spin density will still win. But if we dope the system a little bit away from this perfect nesting, very close to perfect nesting, when we dope it with holes, hole pockets will grow, electron pockets will shrink, and vice versa. When we do that, then the spin density wave, that log, remember, relies on this nesting. And once the nesting is not perfect, that log will be suppressed at some low energy scale, which I denoted here by omega. And so spin density wave coupling will just stop running. And so now we read off whether at that energy scale where this coupling stops running, whether the renormalized Josephson resonance is greater than renormalized interband coupling. And if it is, interband coupling, if it is, then in fact, even though at the bare level we have this inequality, the normalized value is this, and we can simply write down some transition temperature like this. And so this proximity to a spin density wave is what saves the day for this plus minus superconductivity. This has been calculated in many different ways, using many different methods. By our group using a more elaborate version of this, which is sometimes called poor man renormalization group, or German law, poor woman renormalization group. It has been done by Chubukov using so-called Parquet equation, which is another version. And it has also been done by several groups using what is called functional renormalization group. And I'll be delighted to talk about this. If you want, particularly when you do functional renormalization group, you include, I think, 61 million vertices, no channels, and you just solve the problem numerically. But the solution, as it pertains to this plus-minus superconductivity of purely electronic origin, is captured by this. This is the physics of this solution. If you're not close to spin density wave at the parent compound, if nesting is just not there at all, you will not get this kind of superconductivity. You will just have a Fermi liquid with potentially some cone latitude instability at some very, very low, ridiculously low temperatures. You need proximity to a spin density, and therefore you need moderate nesting for this to work. If you have too much nesting, like in a parent state, you'll end up with a magnet. And so this is the story, and I just end here by actually showing some experiments which show very nicely that as you dope, you change the degree of nesting. These are from Hongding's ARPES. If you dope the system, you start with very well nested, that's simply spin density wave. Then the material gets to be less nested upon doping, and spin density wave goes away. But then comes superconductivity, and as the degree of nesting further declines, superconductivity is slowly lost. Once you lose the bands at the Fermi level because you doped too much, then you just end up with electron ones, and holes are gone. You end up with no superconductivity. So I really apologize for taking too long. But anyway, it's a complicated subject, and most of you are hyper fancy theorists. So I hope you'll find it. Thank you.
get when the central mass phase is disordered, but you still have the clearance in the relative phase?
Okay, so in that theory, the question was, what happens in this intermediate regime? Where, so in fact, if that's okay, I'll very quickly go to that slide so everyone can see the content of your question. The question was, what happens when the central mass phase, so to speak, is disordered, but the central mass phase is disordered right here, so we are not in a superconducting state, but this relative phase is still ordered. That's a very good question. So this theory basically has three phases: superconducting, antiferromagnet, and pseudogap. This is a pseudogap. And so in this phase, there is a D-wave pseudogap of pairing origin. It has nodal excitations, but it is not superconductor, and therefore it turns out these nodal excitations are not well defined. There is a Fermi surface here. So if you remember talks from yesterday, you could have a Fermi surface or Fermi pocket, which is still well defined, even though you don't have a Fermi liquid on that Fermi pocket or Fermi point. So what happens in the D-wave case, precisely at the node of a D-wave case, you have a Fermi point. And quasi-particle there is described by Fermi liquid and has some finite Z factor. What happens here, you still have a point. But at that point, there is no pole in the Green's function. There is actually a branch cut. So you have nodal excitations, but they are not defined as well as a Fermi liquid. They have a small anomalous dimension. And this anomalous dimension is brought about by the interaction of these nodal quasi-particles with unbound quantum vortex anti-vortex fluctuations, which it turns out can be described in the form of a gauge field, which is massless. Does that make sense?
Actually, I want to ask slightly different issue.
Okay.
So, I mean, is this kind of mechanism implying that somehow the phase stiffness for the central mass phase and the relative phase is somehow different?
Yes, it does.
I mean,
Yes.
how would that come about?
It comes about because any stiffness to these fluctuations comes from kinetic energy.
Yes.
Without kinetic energy, you'll just have wild fluctuations, which is an antiferromagnet. Once you have a kinetic energy, so remember I had this, so this is now theoretical discussion. Remember I had a version of the theory in which theta ij is viewed as a gauge field.
Yes.
Kinetic energy acts as a Higgs term for this gauge field. Okay. Now, remember how in a beautiful theory of Shanker and Fradkin, you can take a gauge theory and you can end up with either fundamental representation, nothing, or you can end up with Z2 remnant of the gauge theory once you have a mass term. It turns out this mass term is non-local. This Higgs term that acts as a mass term for gauge theory is non-local and leaves behind an XY part of theta ij. Does this make any sense? The symmetry, once you include, okay, let me try to explain this. So imagine I have a theory like this. This term, which in my case is kinetic energy, acts as a Higgs term for this gauge field. What that means, it produces a mass term. In the simplest case, that mass term would have simply be cosine Aij. Then there is nothing interesting. In the less simple case, which is a real superconductor, I get 2 here, which means I get in a situation which describes Z2, the remnant, after I break compact gauge symmetry as I do with this term, the remnant global symmetry is discrete Z2. If I put n here, the remnant global symmetry is Zn, discrete Zn. Does that make sense? Yeah. But the structure of this term here is like something that gives you cosine Aij plus Ajk. You see? Because it has a non-local structure. When you examine this, you discover this term also breaks in long distance limit, it just acts as a mass, and it breaks compact local gauge symmetry. But the global symmetry that remains is U1. And that's XY model that can be described by words.
So that, because you have the mass term in
Which
coming, I mean, that's important.
coming from kinetic energy, it's not local.
So somehow the average of that, what's inside cosine is like, has Z2, but like it's different.
But the relative one has a full, you see, if you rotate this way, so you rotate this, and you rotate this not this way, but that way,
Yeah.
by the same amount, you can describe full global X1, U1.
I see.
It's a beautiful stuff.
Can I ask a follow-up question, which will be purely quantitative?
Okay.
Because it's understandable that languages like that, like proliferation, vortices, vortex, liquid, they work perfectly, and actually the picture is controlled by closeness to, say, quantum critical, like for example a Mott insulator, and we view it as a work close to the critical,
Yes,
as a work
yes,
in a
exactly.
dual picture and stuff.
Yes.
But in that case, we understand that all this picture takes place close to the critical point, and only close to the critical point we have something special like relativistic, emergent Lorentz invariance and
Yes.
stuff. All these things, they happen close to the critical point. So
Yes.
the small parameter is just closeness.
Yes.
And it looks like here on the phase diagram you have this vortex liquid everywhere, even away from the critical point. So is there some understanding of why such a phase, which seems to be a critical one, extends just to a finite distance?
So that's a very good question. And the answer is such that both me and you are partly right. Basically what happens, there are two answers to that. If you look at high energies, and you come down from high energies, you in fact have not quantum critical point, but quantum critical phase. Because this situation where you have nodal excitations, which are not Fermi liquid, but are decohered by a massless gauge field at the nodes, describe a quantum critical phase. It's not a point. It's a phase, and therefore it will be valid everywhere at high energies in a finite range of doping. As you come down, these nodes will move in K-space in general as you change doping. But the theory remains a quantum critical unitary type theory. But you are right too. If you look at lower energies, what's going to happen, you see, to lock these Cooper pairs into particular situations so that long-range superconducting order is gone, they will have to form some form of superlattice.
But basically it's just the other way of reformulating my question. Why, what parameter controls this, just this difference of scales between the reforming of the pairs and just having some...
So there is a paper of mine that you can read, but the sharp answer is, here is actual superconducting transition.
Yes, yes.
And here is a transition where Cooper pairs become well-formed quantities. So there is an enhanced Nernst response. So everywhere on the scale below this, you have this effective view. But when you go here, it turns out it matters a lot whether your doping is 1/8 or different. 1/8 is magical because it allows you to fit a checkerboard of Cooper pairs into a square lattice. At doping 1/8, 2 holes can fit into 4x4 16-side whatever. It doesn't have to be even 4x4, it could be 2x8 or 1/16. And so this is a magic fraction at which, in fact, superconductivity will disappear even at lowest temperature. So everywhere here you will see, as far as fermions are concerned, a quantum critical-like behavior, which at finite temperature will give you these famous arcs, but as the temperature goes to 0, it will shrink to a point. But in terms of a state of Cooper pairs, there is a magic fraction at 1/8, and then some neighboring magic fraction. The strongest one is at 1/8. So in fact, what may happen is that you will get locked into 1/8, and all additional holes or additional electrons will in fact go into domain wall-like superstars. Does that address what you were concerned about?
Partially, because still I really want to understand what's the small parameter. Like 1/8 is the small parameter.
Well, the small, you see, the small parameter is really this. You see, there is some mean field loss of superconductivity. And as you are approaching this everywhere here, you see this electronic criticality. Whereas if you are at zero temperature or very low temperature, you edge toward it through a sequence of magic fraction to magic fraction transitions.
This is exactly my question. There are two different temperature scales. T star when you have preformed
Yes,
pairs,
yes.
and this temperature you keep just referring to this very low temperature. And my
Yes.
question is why the ratio is small or large? Is there some small large parameter? Is there an understanding of why?
There is, yes, there is. So you can compute that. And as you know,
It's a
the
number.
problem is just a number. It's just a number. In strong coupling,
I see.
there is no small things.
Right, but there is some number which
There
just-
is a number.
I see.
You see, I am betting, you see, I'm an old man. My brain cells have all died off. So I'm just praying that this number is large as opposed to small in the favor. But it's just a number. It's like a fractional quantum Hall effect. There is nothing small. They are just numbers. So if you guessed right the structure of the ground state, that means that number is big or small as you want it. It's just a number. I can compute it, you see, but it's, you know, there's a plus minus pi uncertainty. And if you work in units where pi is equal to 1, everything is the same.
So what is the mechanism, I don't know if you can point a mechanism, that allows these Cooper pairs not both condense at zero temperature in that QED3 region?
There are two mechanisms. One is that they get locked into a lattice. So at magic fractions, the motion is so weak, the kinetic
So
energy.
away from the fraction, away from the density wave. Any,
Well, when you are close to this pair density wave, the attraction is so strong that you may go there by a weak first order transition. So you preempt any other fraction but 1/8. The excess holes or electron just go into domain walls, which are far
but they
away.
just crystallize. Is that
So it's a form of crystallization, but very, very soft crystal, because these Cooper pairs are very extended. Remember, they have nodes in the K-space.
okay? So you would in this
There is
language.
the second mechanism is they just fall apart. And
Okay, over there, yes. I'm talking about in pseudo gap.
So
your
here it's
explanation.
basically
So that
a form
means
of crystallization.
in qualitative terms, your explanation of pseudo gap is a mod insulating phase.
But with gapless fermions.
With
That makes a
gapless
big
fermions.
difference. That makes a big difference. So it's a theory, for instance, whose spin response is very non-trivial.
Okay, but that means it has to coexist with a conventional order, density wave order. Like
There is
there's
some
no-
checkerboard order.
There's no pseudo gap. If the checkerboard pattern is gone, you don't see any more anything in neutrons or anything in
Then it's either
SEM.
superconductor or some
Right.
form of maybe antiferromagnet.
Right. So there's no pseudo gap without it. Okay.
It's just a pleasant sense to